I have absolutely no idea why I was invited here with that talk, right? I think it's all about liking me, just because they wanted me to talk here about quantum computing. Not exactly DevOps, cup of tea. I try to do my best. All right. If you look at this graph, it looks like something is getting more and more interesting, as opposed to this other thing, blue on this graph. And this is just Google Trends, right? Nothing special. And I decided to run the query for two terms. One was DevOps. The other one was quantum computing. Who would think that the DevOps is a blue line? Yeah, right. You are exactly right. Nobody, right? So quantum computing looks like it's on the decline, and it's in fact something which is perfectly understood. If you think about any technology changing, you'll get hype. Meaning, should I just stay here, or, yeah. You'll get hype first, meaning the growth of the interest as measured by Google Trends will skyrocket. That's this exponential first step of any new technology. And you know, I'm old enough to go back to several of the past technologies, and they all went through the same pattern. So that period for quantum computing is done and over. So beyond the peak, in the thorough after that, and actually it starts, and you can guess this almost, this almost flat line is actually trending slightly upwards as more and more money is pumped into the system, and the more. Maybe I'll just switch this off and speak loudly or something. Can you hear me? Yeah. All right, so I'll just stay here, old style, and maybe it will work. More and more money is pumped into the system, and the IBMs, Intels, and Googles of this world decided to invest in this technology. Invest not in the sense that they're expecting any results coming financial reporting period. It's just securing their position for something which are extremely risky, might prove to be the future of the large-scale computing. And as I said, it happened before, it didn't succeed, all the cellular automata machines, right? Eventually, Moore's law caught up with the needs, and whatever we need, we can actually calculate on compute on classical church Turing machines, even if there's clusters of them which you work with in your daily jobs. So those definitions are not mine, just don't bother reading them, read the bold only, ignore the small print, right? Every computer we run those days is a quantum computer. Transistor is essentially a quantum device, especially the newer kinds of transistors used in nowadays processors and memories. But the true quantum computer, and I'll get to where we are, in my opinion, in that path, will be the one which could use the quantum features of the world and can exploit the quantum physics in such a way as today's computers exploit the classical physics. I'll get into that thought and ignore all the intermediate definitions. They are of interest to academia, but not much beyond this. So my conviction that something will happen stems from Moore's law, right? I know that the poor guy invented that, meaning something completely different, essentially the yield of the production of chips of particular complexity from the wafer when you print them onto the silicon wafer. But it turned out to be pretty universal in a sense that the capabilities of technology, as far as the size of a area needed to hold a single bit of information, as well as speed of transitioning that bit from 0 to 1 or vice versa, increases logarithmically. So the size actually decreases, but the speed increases exponentially. That's more or less Moore's law. Except that this beautiful straight line in the log-log scale, it's good to measure stuff, right? So if you plot the technologies since the ENIAC or even before that, and plot the area needed for storing a single bit, and you plot the speed on the same graph or the other, it looks exactly the same, you'll see that this straight line goes, again, in the log-log scale, straight line meaning power law. This straight line touches the horizontal axis in something like 2023, meaning something will happen. We can't go beyond that. What does it mean? About that time, you'll be able to store a bit of information on a single atom. Meaning the technologies, as when I started, just let me digress for a second. When I started that work, I was faced with pretty cool problem of building a trigger system for large particle accelerator in DAISY in Germany. At that time, fastest memories had access time of 120 nanoseconds. And extrapolating Moore's law, the designers of the accelerator decided that the one interesting event will be had in every something like 90 nanoseconds. And they built that thing, right? It was huge. It meant flux of electrons and protons colliding, all the supercooling, superconducting magnets. You name it, we had that. Except that technology didn't move that fast in that particular bit of time. So 120 nanoseconds access time of memory, and decision to be made every 90 nanoseconds. Looks tough, right? So at that time, I might be mistaken, it was like 70 nanometers, the technology used. Nowadays, Intel experiments with 7 nanometers. So that's the progress. The smaller the chips, the faster they can get, right? Except that they use much more energy just because you need to run them with a higher frequency. So we managed actually building this stuff out of non-standard memories, bit slice logic, ECL, emitter-coupled logic. That thing was fast, but used tons of energy. And I do believe that with quantum computing, we are about in that space, meaning experiments run by those firms and companies which decided that they don't want to be left behind with the outdated technology when everybody else moves forward. So there's a magic in quantum computing. People talk about that, well, less and less, apparently, but still, they do. I don't know how many of you paid attention to your physics lessons back in the high school. Well, essentially, they try to make unnecessary mystery out of quantum. All this magic about spooky action at the distance, all this magic about true randomness of the result. Well, it's not necessarily that. And I don't want to get into the into discussing physics here. So from our perspective, and I'm saying our consciously, meaning I'm on the other side, I'm not physicist anymore, still, we are dealing with data, and we have operations we can execute on this data. And data and quantum computing has two important things. One is that we operate on entangled states. And you know, if you think that it is difficult to understand, you are in the good company. That's something which prompted Einstein to call certain experiments, or thought experiments, spooky action at the distance. Actually, imagine that in the register, like the usual register we use in the memories or whatever that is inside the processor, you can hold a pattern of all the bits of that register. Seems normal. Except that in the quantum realm, this interaction between the state of the least significant bit and the most significant bit and all the bits inside can be held together and preserved through the operations. If you think about this, it's like 16-bit register can hold 2 to the 16th power simultaneous states. And since, unlike what you might infer from the popular notion of quantum mechanics, this bloody thing is perfectly linear, meaning you act on superpositions. So any combination of the states of the register can be manipulated in the single operation. Seems like the perfect word. And this is exactly predictable, fully deterministic, nothing spooky, except that this entanglement thing looks really, really strange, right? Preserving the pattern if you don't act upon this, preserving the superposition of those patterns. So essentially, what we get is the architecture which can hold many more states, exponentially more states than a single register of today's computers. You would say, whoa, now I have an easy way of doing all the calculations, right? I present my data in such a way that they form those superpositions of entangled states, and I run my operation in one go. So all the NP hard and NP complete word seems simple, right? Test is easy, right? So imagine all the calculation built in such a way that I do just the test. I build my data set, and I do all the tests in one go, right? It would be really, really beautiful. And the first part is doable. The first part, the deterministic part, is a consequence, sorry for the bad word, of the Schrödinger equation, perfectly linear, perfectly. In that sense that, you know, no errors. This register can't be in any other state, right? It evolves in time, and it just does it. The physics experiments are precise, testing that thing, are precise down to 12 digits, right? Extremely precise G-2 experiment. Perfectly linear. Seems beautiful. Except that when you try to read this out, then all the spookiness of the quantum mechanics comes into play. You'll get just one of those states. If they are orthogonal, you measure, you get one of them. Meaning, if you had exponentially many, your chances of getting the solution to your NP-complete problem are just exponentially small. No dice, right? Clever people like Groover, clever people like others working on those problems show that actually, if you are really, really clever, you can get something like the square root of speed up, meaning something which will be linear will take just a square root of the size of the register, of the number of data sets you are working with. That's Groover result. Unstructured database, and selecting on the quantum computer, selecting a single element which is a solution. The other clever guy, something which might be really closer to our everyday's word, Peter Shor. He showed that the problem, which is the root of the security, RSA, namely factoring large integers, is doable in the polynomial time on the quantum computer. So if anybody builds that thing, actually, a real one, like in the metal, then all the security as we know it is gone, just because factoring is easy. And this is a basis of the public key infrastructure, which everybody, almost everybody is using. Not that there are no ways of actually making the system secure again, right? Still, the current security system is susceptible to the attack using quantum computer. So, recap, unitary transformation, evolving system in time, more like rotations in multidimensional space. Doable. Tricky measurement, reducing that whole complex system into the single outcome. If you measure a single bit, you'll get the single outcome of this bit and everything else in the rest of the register which is compatible with that measurement result. And the probability of getting that result is proportional to the square of the sum of the numbers which are compatible with that one. So it will be tricky. Nevertheless, the important thing, and the scientists in that area say about that BQP in relation to NP. BQP is bounded probability of error quantum polynomial time. Nobody has proven yet that actually the relation between those two classes. And that's, in my understanding, is the reason why the big companies are betting on this solution, just because the square root they could get, which is proven by Grover and others, is not enough to justify the huge investment. Now to the practice. What you see now is the result of the IB. Oh, one more thing. And I regret I'll have the slide on that later on. This thing, as you can see, we see chairs, laptops, people around us. This whole world is quantum. Nevertheless, there is something called decoherence, meaning destroying this entanglement which is crucial for quantum computation. And essentially, it reduces statistically to the world we see around us, meaning preserving this spooky, entangled state is really, really difficult. It means your computer has to be perfectly isolated from the environment. If it is isolated from the environment, how do you program this, right? So, well, yeah, it has to be isolated from the environment, except for the moments we want to put the program into that thing. And then we have to preserve that state right after. But as you can imagine, if you switch off and on the protection from the environment, whatever form that has, you are creating tremendous havoc on the system, right? It's like the surge in the network. So you have to correct for errors. And I'll come to guys who claim they don't later on. What you see in front of you is actually a clever idea by IBM. This thing is actually done in metal. This is 4-qubit, I would say, chip, which can be connected to many more. And this thing can correct errors. Previously, I don't want to go into details. There were two kinds of errors. Something which, by the way, again, let me digress for a second. When people first built integrated memories, they were really, really concerned about preserving the information there. So dynamic memories first, but also the parity checks and the correction systems. 8-bit memories for years had actually 9 bits. And the 9th bit was there to check for the parity error. There were systems much more involved than that, but the problem for quantum computing is much more pronounced. And usually, again, not only the bit flip, which was known for some time for usual memories, but also phase error, meaning the wave function, sorry about physics, wave function shifts by some phase uncontrollably as a result of interaction with an environment. This is also an error. And all the systems, it's provable, and actually the experiments have been made. If you do the linear, if you set your qubits in the linear fashion, you can correct just for one of those two errors. And those guys were clever enough to actually build something which has the planar architecture and can correct for both the phase and bit flip errors in the same time. And this thing actually operates. If you want to go into details, how does it work? Essentially, it is a loop where, of superconductor where the current flows. And this loop is broken in two places with Josephson junctions, which essentially are switching elements. They can switch the current on and off, and they can change by switching differently, change the direction of this current. Once they are off this circuit, then the current and the superconducting current just stays there until the whole thing decoheres and you lose all your calculation. So this is breakthrough this year, like March, I guess, but there were others before that. This one is something which originated from the University of Santa Barbara in the US. John, sorry, the name escaped me right now. His group created another array of self-correcting memories, and they use like 9 bits to have 4 real qubits of information. And again, superconducting, isolation from environment, and I'll tell you how much you really need to isolate on one of the further slides. This is new, and here comes something which is really old. Well, if something can be old in that word. If you've heard about quantum computer, you most probably would hear about the D-Wave, Canadian company, Geordie Rose, claiming for years that they've built a first quantum computer. I have bad news for you. This is not a quantum computer. What they actually built was the specialized hardware which can do one thing. It can do that one thing pretty well, but that one thing is the optimization by simulated annealing. And the debate is on whether this thing actually uses any quantum effects. Jury's out. There is some indication that indeed it does, especially tunneling, like something which we knew from quantum equipment for quite some time. Anything which does tunneling transistors is using that effect, right? But their claim is that they can get entanglement. Originally, even really renowned scientists confirmed their claim. However, there was a clever guy, I think Armenian by birth. So when the D-Wave benchmarked their annealer against the best solution on the classical computer, they claimed that for one particular distribution, they were like 3,600 times better. Wow. At least, you know, if we roll back, you'll see one of the definitions. A real breakthrough, we do at least one thing significantly better than possible classically. Wow, we have a real quantum computer, right? It's not a computer, it's not universal, it's annealer. It has particular interaction between the qubits. Still, it looked like it was able to perform one thing significantly better than anybody else. Except that this guy came in and tuned a little bit the commercially available program for simulated annealing. And guess what? You could get that kind of performance, which Google, NASA, and others get for $15 million a piece on a laptop. So I don't believe that the D-Wave system actually is a breakthrough. They use particular method, which is quite clever from the physics point of view, but it is not a breakthrough. And their system is pretty noisy. I think I'm missing one slide here. Sorry. Let me see if I got that in the original version. No, it's lost, so I'll try to describe that in words. Essentially, they went into a lot of work doing... Is that better? They went into a lot of work doing all the stuff which we will be busy with in the future, namely building the environment so that so their computer can work. They have temperatures which are a fraction of interstellar vacuum, right? They have magnetic flux at a fraction of 1/1000 of the Earth magnetic field. So essentially, they managed to isolate the machine from the environment. It takes like 2 days to cool that whole thing. The chip is about this big, and the cooling box you've seen on this slide here, right? This D-Wave, you see the usual rack you work with, right? On the right-hand side. On the left-hand side, you see how much bigger is the D-Wave computer. Essentially, this black thing is a gigantic fridge, right? Yeah, it cools down to the fractions of the degree of Kelvin, but still, it is a fridge. And the chip inside is this big, and the version which will run something like $15 million is just 512 qubits. And let me quote from memory, since I somehow lost the slide. They claim that their coherence time, something which is important, you want the longer the better. And the other guys, IBM, Santa Barbara, are getting to microseconds, or hundreds of microseconds of the coherence time, meaning you can keep the system in the state you want it in for hundreds of microseconds, right? So fractions of a second. D-Wave has something like 100 nanoseconds here. And they claim it's not a big deal just because their system will stay in the ground state, whatever. It's not true. Essentially, this ground state is surrounded by many almost solutions, and that makes actually a really, really big difference. So if you want to take one thing out of this talk, that would be this. For all we know today, quantum computers will not solve hard search problems by using superpositions to try all the candidate solutions at once. There's a ton of work, but this work is happening as we speak. And I'll put my bet, if not of everything else and technology, on the continuity of Moore's law, and I'm expecting something really, really cool and interesting to happen by 2023. With that, if you have any questions, I'll be trying to answer them. If not, that would be it, folks.
Yeah, question. Have you heard about the HP project, The Machine? It's the project from HP company, The Machine. It's like they solve, well, they bet on the old technologies, meaning, but combining them together and making a new environment to work on this. They claim that they will have solution in 10 years. They will have I think fiber optics, also memristors, and something like that. So old solutions, but combined together. So who do you think is going to win?
Well, actually, the optical computers, they were state of the art quite some time ago. It looked promising. And if that's what they do, well, there is a natural limit of the speed of light for communication, meaning you can build a larger data center, but the speed of that will be limited by the communication between the processors, right? On the single processor, well within the scale which is accessible to the communication with the speed of light, you'll get bitten by the Moore's law, meaning single atom for a memory, and the energy like a single electron changing orbit for switching on and off. And that's something which we are bound to see one way or another. So I do believe that taking into, even with that D-Wave thing, they don't really know whether they exploit any other quantum effects beyond the tunneling. Tunneling is a common day technology, right? Tunneling transistors, they just work, right? But the scale and the constant need for speed and smaller size will eventually get us to the place where you can't avoid the quantum mechanics in its full might. And answering directly your question, I haven't heard about the machine project by HP.
Okay, thank you.
All right. So I knew it wasn't the best talk for that one. So guys, be happy with what you see, or just not now. Be happy with what you see here, and all the best for the remaining part of this conference. Thank you very much.